Ancient Rome sustained 1 million people without a single electric light or garbage truck. We tend to fixate on the grand monuments above ground, but the real secret to their success was buried. This video reveals the hidden infrastructure beneath ancient cities that made urban life sustainable. By the end, you will see our modern urban challenges in a completely new light, armed with timeless solutions. How did desert capitals like Petra slake the thirst of thousands? And what kept vast cities from collapsing under their own waste? We will journey into subterranean waterways, through brick sewers older than the pyramids, and across hidden roads carved into bedrock. These silent systems were the lifeblood of civilization, and their principles of design hold urgent lessons for our own crowded, resource-strained world. What forgotten ingenuity lies directly beneath the streets of our oldest cities? The true measure of a city's greatness was not its tallest temple, but its deepest drain. To understand how ancient societies supported populations that would challenge many modern towns, we must first look down, not up. We are talking about hidden infrastructure, a term that goes far beyond simple bricks and mortar. This was the deliberately concealed, often subsurface network of systems designed for the most essential urban functions. Water had to flow in, waste had to flow out, goods and people needed to move, and all of this had to happen without constantly tearing up the streets or poisoning the population. While kings commissioned glittering palaces for their legacy, unknown engineers were solving a far more urgent puzzle: how to keep a dense community alive and water. Water is the non-negotiable foundation. A city in a desert valley, surrounded by towering red cliffs, seems like a contradiction. Petra, the capital of the Nabatean kingdom, thrived for centuries in what is now southern Jordan, a region where rain might fall only a handful of days each year. Yet here, a population of thousands built temples, tombs, and a vibrant trading hub. Their secret was not magic, but a profound mastery of the first principle of hidden infrastructure, the absolute control of water. Without a reliable, clean supply, any urban settlement would wither. Ancient engineers understood this with a clarity that modern city planners are only now relearning. They became experts in hydrology, the science of water's movement and distribution, long before the word was formally invented. Their goal was to capture every precious drop, channel it from distant sources, store it through dry seasons, and deliver it reliably to every corner of the city. This required a deep, intuitive understanding of the landscape. They had to read the land like a map, identifying natural catchments and calculating gradients so water would flow using gravity alone, without a single pump. In Petra, this meant turning the city's greatest threat, the violent seasonal floods that roared through the narrow canyon called the, into its greatest asset. The Nabateans did not just build walls to keep water out, they built a hidden network to invite it in. They carved intricate channels and diversion dams directly into the cliff faces, guiding the floodwaters into a series of underground cisterns and massive reservoirs. One such reservoir, hidden behind a dam, could hold nearly 1.5 million gallons. This was a proactive, anticipatory system. They did not wait for drought to strike. They engineered resilience into the very bones of their city. The water was then distributed through a network of ceramic pipes and stone channels, feeding public fountains, private homes, and even lush garden courtyards. This principle of centralized collection and public distribution was revolutionary. It meant that access to clean water was not a privilege for the wealthy, but a communal right, a cornerstone of public health and social stability. The Roman Empire scaled this principle to an astonishing degree, bringing water from mountain springs over 50 miles away through networks of aqueducts, many running underground to maintain a steady temperature and prevent contamination. These systems were monuments to patience and collective effort, projects that took generations to complete. They prompt a quiet reflection for our own time. How do our modern megacities secure their water? We rely on energy-intensive pumps, chemical treatments, and vast, vulnerable pipelines. The ancient approach offers a lesson in elegant simplicity, using gravity and landscape intelligence to create self-sustaining flows. Their mastery of water was the definitive first step, the silent, flowing lifeline that made every other urban achievement possible. But once the water flowed in, another equally pressing question arose, a question that would demand its own hidden, and perhaps even more ingenious, network of solutions. But water's journey through a city is only half the story. Once it flows from a fountain or a household cistern, it must go somewhere. The true test of an ancient metropolis was not just how elegantly it brought water in, but how efficiently and safely it took out. This is the second, often unglamorous principle of hidden infrastructure, the art of sanitation. In a dense urban environment, waste is not just a nuisance, it is a silent, invisible threat. Without a system to manage it, a thriving city can quickly become a breeding ground for illness. Long before modern germ theory, ancient engineers grasped this fundamental connection between cleanliness and public health. Their solution was not to ignore the problem, but to build it into the very design of the city itself. Consider the cities of the Indus Valley civilization, which flourished over 4,000 years ago. Here, archaeologists have uncovered something remarkable. Individual homes, even modest ones, often contained dedicated bathing areas and latrines, but the real genius lay in what happened next. These private facilities did not drain into a simple pit. Instead, they connected to a sophisticated, city-wide network of covered drains running beneath the streets. These were not open gutters. They were carefully constructed channels made of precisely fitted, baked bricks, designed to carry away from living spaces and out of the city. This was a deliberate, engineered separation. It recognized a simple but profound truth: clean water and dirty water must never mix. By creating a dedicated, subterranean pathway for waste, these ancient planners protected their supplies and created a baseline of urban hygiene that would not be matched in many parts of the world for. It was, in every sense, a public health revolution baked into the city's blueprint. The Romans later scaled this concept to an almost industrial level with the Cloaca Maxima, the Great Sewer, which began as an open drainage canal and was later vaulted over, becoming a hidden, flowing river beneath the city streets. This systematic removal of waste was not about luxury or convenience for the elite. It was a communal necessity. It allowed populations to live in close quarters without constant threat from the very byproducts of their own existence. It prompts a sobering reflection on our own modern systems. We have engineered miraculous ways to treat, but we often take the entire cycle for granted until a pipe bursts or a treatment plant fails. The ancient model reminds us that sanitation is not an afterthought. It is a core pillar of civic design. It requires foresight, investment, and a commitment to keeping the vital flows of a city separate and managed. This intricate dance of bringing water in and guiding waste out define the healthy heartbeat of a city. But to truly thrive, a metropolis needed more than just water. It needed to move people and goods with relentless efficiency. This demand would give rise to a third, equally hidden principle, one that connected empires and powered economies from beneath the ground. The graceful arches of a Roman aqueduct are one of history's most recognizable silhouettes, yet we often miss their true purpose. They were not monuments, but machines, part of a vast, hidden plumbing network that operated on a single, silent principle: gravity. To achieve this, Roman engineers performed a feat of long-distance precision that seems almost impossible with their technology. Their goal was to capture pure spring water from distant mountains and guide it into the heart of a thirsty city, maintaining a steady, gentle flow the entire way. The critical tool was a simple but brilliant wooden frame with a water-filled groove. By sighting along its level surface, surveyors could calculate a gradient so slight it often dropped only a few inches over a mile. This meticulous calculation was everything. Too steep and the water would rush violently, eroding the channels. Too flat and it would stagnate, a lifeless trickle. They had to find the perfect, almost imperceptible downhill path across dozens of miles of rugged countryside. The iconic arched bridges we admire, like the majestic Gard in southern France, were actually last resort structures. They were built only when the channel needed to cross a deep valley, maintaining that crucial, unbroken slope. For most of its journey, the aqueduct was a hidden conduit, tunneling through hills or running in a covered trench just below the Earth's surface, protecting the water from evaporation and contamination. The scale of this achievement is staggering. The aqueduct serving the city of Rome, the Aqua, brought in over 100 million gallons of water every single day. This torrent of clean water was the lifeblood of urban density. It fed immense public baths that served as social hubs, flushed the city's sophisticated latrines, supplied countless private homes through a network of lead or ceramic pipes, and filled public fountains where everyone, rich or poor, could draw their daily supply. The aqueduct transformed water from a scarce commodity into a public utility, a civic right that enabled Rome to sustain a population of over 1 million people. It stands as the ultimate expression of the second principle, the mastery of distribution at scale. This was infrastructure that became a symbol of civilization itself, demonstrating that reliability and grandeur were not opposing ideas, but could be woven into the same flowing stream. It prompts us to consider what our own civic symbols are, and whether they serve the people as selflessly as those silent stone channels once did. But water and waste systems, for all their brilliance, addressed a city's internal needs. For an empire to function, it needed to move armies, messengers, and mountains of goods with impossible speed. This demand would push ancient engineers to create a hidden network of a different kind, one that did not carry water, but the very weight of imperial ambition itself. Rome's iconic aqueducts delivered a river of clean water every day, but that river had to go somewhere. The true measure of their engineering genius is not just found in what they brought in, but in what they courageously and meticulously carried away. Flowing beneath the heart of the ancient city, a hidden river of a very different kind did this dirty, essential work, the Cloaca Maxima, the greatest sewer. Its story begins not with imperial grandeur, but with a practical problem. In the 6th century before the Common Era, the low-lying Forum was a marshy, flood-prone basin. The early Romans, under the direction of their Etruscan kings, performed a foundational act of urban taming. They channelized a natural stream, directing its flow and beginning the process of draining the land to make it habitable. Over centuries, this simple drainage ditch was transformed. It was deepened, widened, and eventually vaulted over with massive stone blocks, becoming a hidden subterranean canal. This evolution is critical to understand. It shows infrastructure adapting and growing alongside the city itself. The finished Cloaca Maxima was a marvel of utilitarian engineering, large enough for a small boat to navigate, and it served a dual, brilliant purpose. First, it collected and runoff from public latrines, baths, and even some wealthy homes, channeling it directly into the Tiber River. Second, and just as importantly, it acted as a colossal storm drain, mitigating the regular floods that threatened the city's civic center. This was infrastructure with two jobs, sanitation and flood control, woven into a single flowing system. The Romans were famously proud of this achievement. The historian Pliny the Elder gazed into its depths and declared it more impressive than the pyramids, a testament to its overwhelming scale and civic necessity. But pride alone did not keep it functioning. Maintenance was a constant, recognized priority. Officials like Sextus Julius, who later oversaw Rome's water supply, documented the need for regular cleaning crews to prevent blockages. This reveals an early, formal awareness of a universal truth. Infrastructure is not a one-time project. It is a perpetual commitment. The Cloaca Maxima symbolizes a profound and humble acknowledgement. A city's health, its very ability to endure, depends as much on what it removes as on what it provides. It was the city's hidden circulatory system, carrying away the inevitable byproducts of life at scale. This concept that waste management is not a disgraceful chore, but a dignified pillar of civilization, echoes far beyond Rome. It prompts us to look at our own cities, to consider the immense, invisible networks that process what we leave behind. How do we honor that necessary, unseen work today? The Roman answer was to build for the ages and to dedicate public resources to its care. Their great sewer stands as a monument to a clear-eyed truth. Sustainability requires dealing with the entire cycle, not just the pleasant half. And while Rome's solution was monumental, other ancient cultures confronted the same challenge in remarkably different, and sometimes even more elegant, ways. A city's skeleton is found in its street plan. While Rome's Cloaca Maxima dealt with the consequences of dense living, other civilizations approached the challenge from the opposite direction, designing their cities from the ground up to make such systems not just possible, but elegantly simple. This brings us to the third, overarching principle of hidden infrastructure, integrated urban planning. In places like in the Indus Valley or in central Mexico, we see that the most sustainable systems were not retrofitted into chaotic layouts. They were baked into the original blueprint. The famous grid pattern of these cities, with their wide, straight main streets and orderly side alleys, was far more than an aesthetic choice. It was of logistical foresight. This rigid geometry created predictable pathways, making it infinitely easier to plan, construct, and maintain the subterranean networks of water and waste. A wide central boulevard was not just for grand processions. It often served as a designated corridor, concealing the largest water mains or drainage channels beneath its surface. Arteries hidden directly below the civic veins. This was a holistic philosophy of urban life. Residential districts, commercial markets, and ceremonial centers were not randomly scattered. They were intentionally zoned in relation to these hidden flows. Artisans working with water, like potters or dyers, might be situated near specific conduits, while temples were often placed at the terminus of sacred water channels. Every part of the city worked in concert with the unseen systems that sustained it. The infrastructure was not an afterthought. It was the first thought, the foundational logic upon which every brick was later laid. This level of intentional design minimized conflicts and maximized efficiency for centuries. It prompts a direct and perhaps uncomfortable comparison to the growth of many modern cities. So much of our urban sprawl has been reactive, expanding in rings around an old core, with utilities desperately patched in beneath existing neighborhoods, a constant game of catch-up. The ancient model asks us to consider the power of starting with the end in mind, of designing not just buildings, but the flows between them. What if we planned our new communities not just for cars and commerce, but first for the silent, essential movement of water, energy, and information? This principle of integrated planning supported every other system, creating a resilient framework that could endure. Yet even the most perfectly planned city on the surface faced a relentless, invisible enemy, one that could undermine all that careful order from below, the constant threat of flooding and erosion. The principles of integrated planning created a resilient framework above ground, but some ancient societies took the concept of urban space a step further, or rather, a step deeper. They realized that a city's capacity was not limited to its surface footprint, and that true sustainability sometimes meant building down. This brings us to a fourth, astonishing principle of hidden infrastructure, the creation of subterranean transport and multi-layered urban design. Beyond managing water and waste, these networks moved people, goods, and entire communities through a hidden third dimension. The rose-red city of Petra offers a stunning initial example. The majestic, that narrow, winding canyon flanked by towering cliffs is celebrated as a dramatic entrance, but it was also a brilliant feat of hidden infrastructure. This was not a random natural fissure, it was a carefully managed, protected trade route. The Nabateans enhanced it, paving the floor and carving channels into its walls to control floodwaters, transforming a geological feature into a secure, defensible corridor for caravans. It shielded merchants and their precious cargo of incense, silk, and spices from the scorching desert sun and potential raiders, a hidden road that delivered prosperity directly into the city's heart. This idea of using the earth itself for protected movement reaches its most breathtaking scale in a place like, in the Cappadocia region of modern Turkey. Here, an entire city was carved downward, a labyrinthine world extending over 200 feet deep. This was not a simple cave network, it was a meticulously engineered underground metropolis. Miles of tunnels connected living quarters, communal kitchens, wine presses, stables for livestock, chapels, and even schools. Massive circular stone doors, weighing hundreds of pounds, could be rolled shut from the inside to seal each level, providing security from invading armies. Ventilation shafts, some plunging over 150 feet deep, provided fresh air to the lowest chambers, while protected wells tapped into the groundwater far below. And its sister underground cities represent the ultimate expression of using subterranean space to expand urban capacity. They provided not just security, but also a stable, temperate environment, shielding inhabitants from the blistering heat of summer and the bitter cold of winter. This was a city with literal layers, a vertical urban plan that used the third dimension, downward, to create redundancy and resilience. It functioned as a complete alternative urban space, a parallel city that could be occupied for months at a time. These hidden roads and chambers force us to reconsider the very shape of a sustainable city. Our modern urban planning is overwhelmingly horizontal, spreading outwards across the landscape. The ancient model of Petra asks a provocative question: are we dramatically underutilizing the space beneath our feet? Contemporary projects like underground rail systems, utility tunnels, and subsurface storage are echoes of this old idea, but they are often single-purpose. The ancient vision was holistic, creating multifunctional, habitable depth. This principle of multi-layered design shows that ancient urban life could literally operate on another level, enhancing sustainability not just through engineering, but through profound spatial innovation. It suggests that the future of our own crowded cities might not lie in ever taller skyscrapers, but in looking downward to rediscover the protective, efficient, and expansive potential of the ground itself. While some cities carved downward for protection, others dug for life itself. In the vast, sun-baked plateaus of ancient Persia, where rainfall was a rare gift and surface rivers often vanished into the thirsty earth, engineers confronted water scarcity with one of history's most elegant and enduring solutions, the Qanat. This was not a grand aqueduct marching across the landscape, but something far more subtle and intelligent, a hidden water mine. Imagine a gently sloping tunnel carved backward into the base of a mountain range. It begins deep within an alluvial fan, that gravelly slope where rainwater from the highlands soaks into the ground, creating a hidden underground reservoir. The Qanat's builders, known as, would first dig a vertical mother well down to this water table, sometimes over 300 feet deep. Then, with an almost supernatural sense of gradient, they would begin tunneling horizontally backward, away from the foothills, for miles. The slope was everything, a precise, gentle decline of perhaps 1 foot for every 1,000 feet of length. This meticulous gradient, maintained solely by hand and simple surveying tools like a plumb line and a water level, allowed gravity to do all the work. It coaxed the groundwater into a slow, steady flow along the tunnel floor, bringing it silently through the dry earth toward the distant plains where it was needed. Along the entire length of this underground river, vertical access shafts were dug at regular intervals, not just for construction and maintenance, but as ingenious ventilation points that prevented stagnation and allowed the precious water to remain cool and clean. After miles of darkness, the water would finally emerge into the open air at the tunnel's mouth, a miraculous spring in the middle of a desert. This was not a sporadic flow, but a constant, reliable trickle, a sustainable tap directly into the aquifer. The Qanat was a masterpiece of patient, communal effort. A single system could take a generation to complete, with knowledge and labor passed from father to son. It bound communities together in a shared, vital project, and the water it delivered was often governed by strict, equitable time-sharing agreements, ensuring that every farm and village along its course received its fair share. This system highlights a profound principle, working in harmony with natural geology and physics rather than fighting against them. The Qanat did not deplete the aquifer, it gently harvested its overflow. It used the earth itself as a natural filter and insulator, preventing the catastrophic evaporation that would have claimed any open canal in that climate. There is a quiet brilliance here that challenges our modern instincts. Today, in arid regions, our first response is often to drill deep, energy-intensive wells and pump water at a furious rate, a practice that can drain ancient aquifers in decades. The Qanat presents a different philosophy, one of careful listening to the landscape and patient collaboration with its rhythms. It invites a reflective question. In our search for high-tech solutions to resource scarcity, have we overlooked the profound wisdom of low-tech, high-impact systems that renew rather than exhaust? These silent, flowing tunnels were more than infrastructure. They were a covenant with a dry land, a promise written in water and stone that life could not just survive, but sustainably flourish. A covenant with a dry land, however, is only as strong as the materials that give it form. The silent water of a Qanat or the steady flow of an aqueduct required a physical vessel, a hidden channel that could withstand the relentless pressures of time, water, and earth itself. This introduces a fourth, foundational principle of hidden infrastructure, the deliberate selection of materials for longevity. Ancient engineers were not just builders, they were master material scientists, choosing substances not for their immediate cheapness or ease, but for their enduring performance over centuries. They understood that infrastructure is a promise made to future generations, and that promise required a physical form that could keep it. The Romans, for instance, faced a constant challenge with their harbor works and the piers of their aqueducts. Structures that needed to stand firm in constantly wet environments, where ordinary mortar would simply wash away. Their revolutionary solution was a concrete that seemed to defy logic, one that actually gained strength when submerged. The secret ingredient was pozzolana, a fine volcanic ash mined from regions like near Mount Vesuvius. When mixed with lime and rubble, this ash created a chemical reaction that allowed the concrete to cure and harden even underwater, forming a monolithic, water-resistant mass. This was not a happy accident, but a targeted application of local geology to solve a specific, enduring problem. It transformed Roman ports into storm-proof havens and gave aqueduct piers an immortality that still astounds us today. Similarly, in the Indus Valley cities the ubiquitous building material was the kiln-fired brick, but these were not crude, irregular lumps of clay. They were standardized, uniformly sized blocks, baked at high temperatures to achieve a hardness and density that made them remarkably resistant to water corrosion. This consistency was not merely for aesthetic tidiness, it was a logistical and engineering. Uniform bricks meant predictable construction, stronger bonding, and walls and drains that could withstand the annual monsoon floods and the constant flow without crumbling into mud. In both cases, from the volcanic hills of Italy to the river plains of the Indus, the choice of material was a direct response to the local environmental challenges. It was an investment, a conscious decision to spend more labor and resources upfront to avoid catastrophic failure and endless repair later. This principle stands in quiet contrast to much of our modern approach, where the economics of initial cost often outweigh the calculus of long-term resilience. We patch roads with asphalt that cracks in the heat, and we lay pipes that corrode within decades, creating a cycle of constant, disruptive maintenance. The ancient model asks us a difficult but vital question: what is the true cost of something built not to last? Their hidden conduits, sealed with volcanic ash or lined with perfect bricks, were physical expressions of a different philosophy, one that measured value in centuries of silent, reliable service. They built for the unborn, ensuring that the vital flows of the city would not be a burden on their children's children, but a gift. This commitment to durability meant that once these systems were established, they could be almost forgotten, operating flawlessly in the background for generations. Yet even the most perfectly engineered physical network is useless without one final, crucial element: the human knowledge and social structure required to keep it alive. Yet the most resilient materials are inert without the human hands that maintain them. The silent, flowing networks beneath ancient cities represent a fifth and perhaps most vital principle: the social contract of shared upkeep. Infrastructure is not a static monument, it is a living system, and its survival depends on a collective commitment to its care. This concept was often formalized in ways that wove maintenance directly into the fabric of society. In the vast Inca Empire, stretching along the spine of the Andes, the road network was the empire's central nervous system. This was not a single path, but over 25,000 miles of engineered highways, with tunnels through mountains and suspension bridges woven from grass cables spanning deep ravines. The brilliance of this system lay not just in its construction, but in its governance. The Inca state did not maintain it with a paid, professional crew. Instead, they instituted the a form of labor tax. Each household in the empire owed a certain number of days of work per year to the state, and a portion of this labor was specifically dedicated to the upkeep of roads, bridges, and storehouses. This meant maintenance was a rotating, communal duty, a shared civic responsibility that bound distant communities to the health of the whole network. Everyone had a direct, personal stake in its functionality, because everyone might rely on it for trade, communication, or security. Similarly, in the Qanat systems of Persia, the role of the tunnel digger and cleaner was a specialized, revered profession. Their knowledge of hydrology and tunneling safety was passed down through families, and communities pooled resources to pay for their essential, dangerous work. This was not an ad repair. It was a structured, valued social role, ensuring the life-giving water would not fail. These systems recognized a profound truth. The greatest threat to any hidden network is not a sudden catastrophe, but the slow creep of neglect. By embedding maintenance into law, economy, and culture, these societies institutionalized foresight. They planned not just for the building phase, but for the centuries of operation that followed. This stands in stark contrast to a modern tendency we might call build and forget, where ribbon cuttings are celebrated, but long-term funding for upkeep is a perpetual political struggle. The ancient model asks us, where is our for the 21st century? How do we cultivate a shared sense of ownership and duty for the invisible systems that sustain us all? It suggests that sustainability is not merely an engineering challenge, but a social one, requiring a covenant between the people and the pipes, the citizens and the sewers. A promise to tend to the unseen, so it may continue to serve the seen. This deep understanding of communal care enabled systems of astonishing luxury to emerge, even in the distant Bronze Age, proving that when the fundamentals are secured, civilization can turn its ingenuity toward comfort. The silent flow of water through a stone channel is a powerful image, but it is a fragile one without constant vigilance. This brings us to a fifth, and perhaps most human, principle of hidden infrastructure, the necessity of maintenance and social organization. A brilliant aqueduct or a perfectly graded sewer is only as good as its ongoing upkeep. The greatest physical works could be rendered useless in a season by silt, a collapse, or simple neglect. Ancient societies understood this intimately, and their response was to formalize the care of these systems, creating what we might call a bureaucracy of care. In Rome, this responsibility fell to the curators of the waters. This was not a ceremonial title, but a high-stakes administrative post held by some of the empire's most capable citizens, like the celebrated engineer Sextus Julius. He did not just admire the water supply, he managed it, documenting its every mile, its flow rates, and its legal statutes in meticulous detail. His teams of state-funded laborers were the unseen heroes of daily life. They patrolled the underground channels, cleared blockages from the Great Sewer, and repaired cracked pipes, ensuring the million-gallon daily pulse of the city never faltered. This was not a set-and-forget project. It was recognized as a continuous, non-negotiable civic duty. The organizational genius lay in making this maintenance systemic, surviving the rise and fall of emperors and the shifting winds of politics. The water had to flow regardless of who sat on the throne. We see similar formalized care in other cultures. In the vast Qanat systems of Persia, the tunnel masters formed a respected guild. Their specialized knowledge of hydrology and underground construction passed from father to son. Villages collectively paid for their essential, dangerous work of cleaning and extending the water mines, a shared investment in their own survival. This principle reveals a profound truth. Sustainable infrastructure is not just about what you build, but about the enduring social structures you create to protect it. It requires an ongoing commitment of resources, attention, and skilled labor, woven into the very fabric of governance and community. It prompts a direct and urgent question for our own time. How do our modern municipalities compare in maintaining the aging, often century-old water mains, bridges, and electrical grids hidden beneath our streets? We celebrate the ribbon cutting for a new pipeline, but do we fund its inspection and repair with the same fervor? The ancient model reminds us that the human element, the administrators, the engineers, and the laborers, is the final, indispensable glue that holds the physical works together across centuries. It is a lesson in institutional sustainability, a recognition that the most vital network of all is the one of shared responsibility, ensuring that the gifts of the past continue to serve the future. The ultimate expression of this social contract may be found not in stone pipes or deep tunnels, but in water and earth on a monumental scale. Beneath the towering stone spires of Angkor Wat, a different kind of temple was built, one of liquid geometry. The Khmer Empire's capital was not merely a collection of grand monuments in the Cambodian jungle. It was a vast, engineered hydraulic landscape. A city designed from the ground up as a machine for living with water. The challenge here was the opposite of a desert scarcity. It was abundance with a violent rhythm. The annual monsoon delivered a deluge, flooding the land, only to be followed by months of intense dry heat. To survive and thrive, the Khmer engineers performed an act of breathtaking environmental choreography. They did not just build a city, they sculpted the very terrain around it into a massive, functioning system. This was the principle of large-scale environmental modification for urban sustainability, executed with staggering ambition. At its heart were the immense, perfectly rectangular reservoirs. The largest, the West, is an artificial lake over 5 miles long and 1.5 miles wide, capable of holding over 50 billion gallons of water. These were not just ceremonial pools, they were the empire's strategic water banks. A sprawling, grid-like network of canals, channels, and moats connected these reservoirs to the urban core and the surrounding farmlands. During the monsoon, this network acted as a giant relief valve, capturing and diverting the floodwaters into preventing the city from drowning. Then, during the long dry season, the system reversed. Gates were opened, and the stored water was released through the canals to irrigate vast rice paddies, transforming the volatile jungle into a predictable, multi-crop agricultural powerhouse. This engineered landscape allowed Angkor to support a population that some scholars estimate was over 750,000 people, making it one of the largest pre-industrial cities in the world. For centuries, the true scale of this achievement was hidden, with much of the canal grid reclaimed by the relentless jungle. But recent LIDAR technology, which uses laser pulses to map the ground beneath the forest canopy, has revealed the stunning, ghostly imprint of this hydraulic city. The scans show a sprawling, low-density metropolis organized around this water grid, with canals running in precise lines for miles, connecting temples, neighborhoods, and farmsteads into a single integrated organism. Angkor was not placed on the land, it was woven into it, a symbiotic partnership between human design and natural forces. This raises a profound and enduring tension, one we grapple with today. The Khmer system was a masterpiece of environmental engineering that supported a magnificent civilization for centuries. Yet, some research suggests that the very intensity of this modification, including possible deforestation and sedimentation, may have contributed to vulnerabilities in the system over the long term. It presents a delicate balance, the need to shape our environment for survival against the imperative to preserve its underlying health. Angkor's legacy is not a simple blueprint, but a complex lesson in scale and consequence. It shows us that the most sustainable cities may be those that see themselves not as separate from their ecosystem, but as a conscious, careful part of its flow, using ingenuity not to conquer nature, but to dance with its most powerful rhythms. The ghostly canals of Angkor remind us that even the grandest systems are not born complete. This reveals a sixth, vital principle of ancient infrastructure: adaptability through incremental development. Rarely, if ever, was a city's hidden network built in one. More often, it grew organically, layer by layer, responding to the immediate needs of the present while leaving room for the demands of the future. The Cloaca Maxima in Rome is a perfect testament to this. It began in the 6th century before the Common Era as a simple, open-air drainage ditch, a practical solution to drain a marshy valley. Over the next 500 years, as Rome swelled from a regional town to a world capital, the ditch was deepened, widened, lined with stone, and finally vaulted over, becoming the monumental sewer we recognize. It was not a single project, but a series of projects, each generation building upon and improving the work of the last. This incrementalism was not a sign of poor planning, but of profound pragmatic wisdom. It allowed for continuous adaptation. Engineers could observe what worked, learn from failures, and incorporate new technologies or materials as they became available. It was a strategy of low-risk, high-reward evolution. Starting small meant that massive resources were not committed to a single, untested design that could become a catastrophic white elephant. Instead, each successful phase funded and justified the next, creating a resilient system that grew in lockstep with the city itself. This stands in quiet contrast to many modern megaprojects, which often aim for a final, fixed solution conceived on a drawing board and then imposed upon the landscape. Sometimes with little room for later adjustment, the ancient approach asks us a compelling question: can our own infrastructure be more modular, more open to graceful evolution? Imagine a water system or a transit network designed not as a finished monument, but as a living scaffold. With interfaces and connections deliberately left open for future expansion or technological upgrades we cannot yet foresee. This evolutionary model did more than just reduce financial risk. It allowed practical knowledge to accumulate. The who maintained a qanat, or the Roman who patrolled the aqueducts, were not just laborers, they were living libraries of hydrological and structural knowledge. Their hands-on experience, passed down and refined over generations, became the city's institutional memory, ensuring that each new layer was smarter and more resilient than the last. The infrastructure itself became a physical record of this accumulated wisdom, a testament to patient, collaborative progress. It was a strategy that built not just for a generation, but for a civilization, making each contribution a permanent brick in an enduring foundation. This principle of adaptable, incremental growth is perhaps the most quietly hopeful of all, for it suggests that the path to a sustainable future is not a single, impossible leap, but a series of deliberate, intelligent steps. A city's stomach was as important as its heart. While aqueducts and sewers managed the flow of water, another hidden system managed the flow of something even more vital: food. The sustainability of any urban center depended on its ability to secure not just water, but nourishment for thousands, year-round, through seasons of scarcity and times of crisis. This demanded a different kind of hidden infrastructure, one designed not for movement, but for preservation. Beneath the bustling streets and grand forums, Ancient engineers created spaces of stillness, vast, cool, dark chambers where the harvest of an entire region could be held in reserve. In Constantinople, the mighty capital of the Byzantine Empire, the famous Basilica Cistern is celebrated for its forest of columns holding up a ceiling that mirrored an underground palace for water. But it was just one of many. The city had over 80 such cisterns, a hidden, decentralized web of liquid security, yet water was only half the equation. Parallel to these watery cathedrals were the granaries, often equally subterranean. These were not simple sheds, but engineered environments. Subterranean silos, like those found at sites such as the ancient community of Qumran near the Dead Sea, leveraged the Earth's natural insulation. Dug deep into the dry, stable ground, these pits or chambers kept grain at a consistently cool temperature, dramatically slowing spoilage and protecting the precious stores from rodents, insects, and the ravages of the desert sun above. This was climate control achieved through geology, not machinery. The principle at work here is one of reserve capacity, the deliberate creation of a buffer between supply and demand. A city living harvest to harvest was perpetually one drought or one failed shipment away from disaster. By building these hidden larders, urban planners introduced a crucial lag into the system. A surplus from a bountiful year could be saved to offset a lean one. In times of peace, the reserves could stabilize prices and feed the population through winter. In times of siege, they could mean the difference between surrender and survival, allowing a city to withstand months, sometimes years, of isolation. These storage systems were a profound acknowledgement of uncertainty. They were an investment in patience and foresight, a communal savings account of calories. The grain silo was, in its own humble way, as critical to urban survival as the fortified wall. One defended against the visible enemy outside the gates, the other defended against the invisible, slow-moving enemy of hunger within. This prompts a direct and urgent reflection for our own interconnected world. We have built astonishingly efficient global supply chains that deliver fresh produce across continents in days. But this efficiency often comes at the cost of resilience. Our systems are lean, with minimal buffers, optimized for just-in-time delivery rather than just-in-case security. A disruption at a single port, a drought in a key growing region, or a conflict along a trade route can send shockwaves through supermarket shelves. The ancient model of reserve capacity asks us a difficult question. In our pursuit of sleek, uninterrupted flow, have we forgotten the fundamental wisdom of the cellar? How do we design modern equivalents of those subterranean silos? Not for grain perhaps, but for energy, for medical supplies, for the essential components of daily life. The hidden granaries teach us that true sustainability is not about constant, flawless abundance. It is about having the depth to endure when the flow inevitably falters. It is the quiet, unglamorous work of preparing for the hard season, ensuring that the city's life can continue even when its visible connections to the outside world are severed. The silent, cool depths of a grain silo guarded against hunger, but another invisible enemy required a different kind of defense. This brings us to a seventh, profoundly human principle, the pursuit of public health as the ultimate driver of urban design. Long before the discovery of germs, ancient societies forged a powerful, intuitive link between their hidden infrastructure and the wellness of their people. They observed that certain conditions, like stagnant water or foul odors in crowded neighborhoods, often preceded outbreaks of illness. The Romans gave this observation a name, miasma, meaning bad air. While their understanding of the cause was mistaken, their prescribed solution was remarkably effective. They believed that flowing water and moving air could cleanse a city of this unhealthy atmosphere. This belief was not mere superstition. It was a practical theory that spurred monumental action. It drove them to build the aqueducts that brought in fresh mountain springs, and the Cloaca Maxima that carried waste away to the river. Every public bath complex, with its steaming pools and elaborate drains, was not just a social club, it was a temple to this philosophy of cleanliness. The result was a dramatic, if unintentional, victory over waterborne diseases. By separating clean water from waste and ensuring constant flow, these systems drastically reduced the transmission of illnesses like typhoid and dysentery that had plagued human settlements for. The infrastructure became a silent, collective immune system for the city itself. This principle reveals a profound truth. The greatest urban innovations are often born from the urgent need to protect the community from shared threats. Urban design was, in many ways, a direct response to the specter of epidemics. Wide streets in grid-planned cities allowed for sunlight and air circulation, while subterranean drains removed the sources of contamination from daily life. This prompts a direct and vital question for our own time. What is the ultimate metric for judging our infrastructure today? Is it speed, capacity, or cost? The ancient model suggests a different benchmark: the health and resilience of the population it serves. Every pipe, every treatment plant, every green space can be seen through this lens. Does it clean the air we breathe? Does it ensure the water we drink is safe? Does it provide spaces that promote physical and mental well-being? The Roman engineer, guided by the concept of miasma, and the modern epidemiologist, armed with data on pathogens, are ultimately striving for the same goal: a city that sustains life in the fullest sense. This timeless link between what we build and how we thrive reminds us that the most vital function of any hidden network is not merely convenience, but care. It is a lesson written in stone and water that the true foundation of a civilization is the health of its people. But the health of a city is not guaranteed by its past achievements. The silent, flowing systems beneath ancient Rome represented a pinnacle of urban thought, yet they were not a permanent inheritance. The story that followed their decline offers a sobering lesson in reverse, a principle of degradation that proves just how fragile this hard-won knowledge truly is. As the centralized power and administrative genius of the Roman Empire fragmented across Europe, so too did the meticulous care for its hidden infrastructure. Aqueducts fell into disrepair, their channels clogged with silt and their arches for new buildings. The Cloaca Maxima, though it never ceased to function entirely, was no longer maintained with the same systematic rigor. In many former Roman towns, the sophisticated separation of clean and dirty water gradually broke down. This was not a sudden collapse, but a slow unraveling, a forgetting. By the High Middle Ages, centuries later, the contrast with the ancient model was stark and telling. In Paris, one of Europe's largest and most vibrant cities, the primary method for moving waste was not a hidden, vaulted sewer, but the open gutter running down the center of the street. Households would simply toss their refuse from windows into these channels, where rainwater was supposed to wash it away toward the Seine River. The system was entirely passive and surface level, utterly dependent on weather. In dry periods, the waste would accumulate and fester, and during heavy rains, the gutters would overflow, spreading contamination. The famous cry of, "a warning shouted before emptying a chamber pot," was not a quaint custom, but a symptom of a profound infrastructural regression. The result was a cityscape where the sights and smells of waste were a constant, public reality, and where the link between sanitation and public health, so intuitively grasped by earlier civilizations, had been dangerously weakened. Outbreaks of illness were frequent and devastating. This period stands as a powerful counterpoint to everything we have explored. It demonstrates that sustainable urban life is not an inevitable state, nor is technological knowledge a one-way ascent. It is instead a conscious cultural choice, requiring continuous investment, dedicated administration, and the preservation of practical skill. The comparison between imperial Rome and medieval Paris is not about judging one era as superior, but about tracing the consequences of a shift in priority. When the social contract of shared upkeep frays, when maintenance is no longer seen as a vital civic duty, the hidden systems that guarantee health begin to fail. The open gutters of Paris were not a primitive starting point. They were what remained after a more advanced system had been lost to time and neglect. This historical interlude is a crucial hinge in our story. It frames the ancient achievements not as distant curiosities, but as solutions to problems that would resurface with a vengeance. The struggles of medieval cities with filth and disease created an urgent pressure, a longing for cleanliness and order that would eventually spark a rediscovery. The very hardships of this period of regression would set the stage for a future renaissance, one where engineers and thinkers would look back, not to the recent past, but across the centuries to the silent, flowing wisdom of Rome, and ask themselves how such a thing was ever done. The open gutters of Paris were a stark reminder of what happens when a city forgets its own foundation. Yet within that very regression lay the seeds of a rediscovery, a slow turning back toward the principles that had once made urban life not just possible, but healthy. This journey of rediscovery leads us to an eighth, quietly brilliant principle woven into all the systems we have explored: energy efficiency and passive design. Ancient infrastructure did not have the luxury of flipping a switch. There were no fossil fuels to burn, no electric pumps to summon. Every solution had to work with the immutable laws of physics, harnessing natural forces as a silent, perpetual partner. This was not a limitation, but the source of its enduring genius. Gravity was the ultimate free engine. It was the invisible hand that guided water down the gentle slope of a Roman aqueduct for 50 miles, and the steady pull that drew groundwater through a Qanat's dark tunnel for even longer. The wind, channeled through cleverly placed ventilation shafts, became the natural air conditioning for underground cities like, breathing fresh life into chambers 200 feet deep. The earth itself served as a thermal battery. The massive stone walls of a cistern or the deep clay of a subterranean grain silo used thermal mass, the property of dense materials to absorb heat slowly and release it even slower, to create a stable, cool environment year-round. This was a symphony of passive forces, a design philosophy that minimized active energy input to nearly zero. The system, once built, simply worked, decade after decade, requiring only maintenance, not constant fuel. This principle represents a profound harmony between engineering intention and environmental intelligence. It is a low-entropy model, meaning it created immense, life-sustaining output, clean water, temperate housing, preserved food, with minimal ongoing resource consumption and disorder. The ancient city was, in a very real sense, a carefully tuned instrument played by the sun, the wind, and the pull of the planet. Contrast this with the hidden veins of our own modern cities. Our water towers rely on electric pumps to lift water against gravity. Our subways and tunnels require massive ventilation systems running on grid power. Our climate control for buildings and data centers demands a constant, voracious flow of energy. We have achieved miracles of convenience and scale, but we have done so by adding layer upon layer of active, energy-intensive systems. The ancient approach challenges this dependency not as a call to abandon technology, but as an invitation to relearn a fundamental balance. Could we reintegrate more passive design into our contemporary urban fabric? Imagine buildings shaped and oriented to maximize natural light and cooling breezes, reducing the load on heating and air conditioning. Consider stormwater management systems that use gravity-fed and retention ponds instead of energy-heavy treatment plants for initial capture. Envision using the thermal mass of the ground itself through geothermal loops or simply smarter building materials to stabilize temperatures. This is not about going backward, but about moving forward with a wiser, more resilient toolkit. It asks us to see the city not as a machine that must be constantly fed power, but as an organism that can be designed to thrive on the abundant, renewable flows of the natural world. The lesson from the aqueduct and the Qanat is one of elegant efficiency, a reminder that the most sustainable solution is often the one that does the most with the least. Turning necessity into a lasting covenant with the forces that were here long before us and will remain long after, a city built upon a lake should not have been possible. Yet the Aztec capital did not merely survive on the waters of lake, it thrived because of them. This was a metropolis that rejected the very idea of terra firma, choosing instead to weave its existence into the fabric of a vast, shallow lake. The challenge here was unique, a logistical puzzle that would have paralyzed less inventive minds. The lake water was brackish, a mix of fresh and salty, unsuitable for drinking or irrigation. Seasonal floods threatened to swamp the island city, while its island nature made expansion seem impossible. The Aztec response was in context-specific design, a hidden infrastructure that turned every apparent weakness into a formidable strength. Their first innovation was often called a floating garden, though it was anything but floating. These were artificial islands, constructed by staking out rectangular plots in the shallow lakebed and weaving fences from reeds and willow branches. These enclosures were then filled with layers of mud scooped from the lake bottom, aquatic vegetation, and rich compost, creating fertile, elevated plots that were essentially permanent, anchored extensions of the land. A grid of canals was left between these garden plots, serving as waterways for canoe traffic and as constant irrigation channels, with the nutrient-rich muck from the canals regularly dredged to replenish the soil. This was agriculture integrated directly into the urban transport network, a self-renewing system that produced multiple harvests each year and fed a population estimated at over 200,000. But they were only part of the aquatic machine. To protect and the city itself from the lake's salty surges and floodwaters, the Aztecs engineered massive dikes. One of the most famous, built under the ruler, stretched for nearly 10 miles. This stone and earth barrier did more than hold back water, it actively managed it. It incorporated sluice gates that could be opened or closed to control water levels, separate brackish from fresh sections of the lake, and even create controlled basins for the. Simultaneously, to solve the drinking water problem, they constructed a dual aqueduct system from the springs of Chapultepec Hill on the mainland. Built of twin clay pipes, this allowed one conduit to be cleaned and maintained, while the other remained in constant operation. Ensuring an uninterrupted flow of fresh water into the cities, many public fountains and ceremonial centers. Every element of this system, from the productive canals to the defensive dikes, was a creative negotiation with a specific, demanding environment. It was a refusal to impose a foreign template, like a desert qanat or a Roman hillside aqueduct, onto a lacustrine world. Instead, the Aztecs listened to their landscape and built a syntax of water and earth that was entirely its own. This principle of hyperlocal adaptation is perhaps their greatest legacy to the story of urban sustainability. It asks us a vital question about our own standardized, globalized approaches to city building. Can a solution designed for a coastal megacity truly work for a desert town or a mountain community? Genius whispers that true resilience is not found in universal blueprints, but in deeply local intelligence, in designs that speak the native language of the land. Turning environmental constraints into the very source of a city's abundance and identity. The genius of the Aztecs was a triumph of local intelligence, but their aqueducts and dikes, like all the systems we have seen, share one final, fundamental ingredient. They were built by countless hands, organized not just by technical need, but by a deeper social force. This reveals a ninth, foundational principle: the role of collective labor and social cohesion in turning vision into stone and water. The Cloaca Maxima did not dig itself, and a qanat spanning miles did not appear by magic. These projects required the coordinated effort of thousands, often for generations. This mobilization of labor was far more than a logistical exercise. It was a profound social project. In many cases, it was organized through state systems like the Inca, a form of labor tax considered a civic duty, or through communal agreements where villages pooled their efforts to dig a life-giving water tunnel. Participating in such a monumental, shared task reinforced a collective identity. It transformed abstract civic belonging into the tangible, aching reality of moving earth and fitting stone alongside one's neighbors. The finished infrastructure, whether a public fountain or a hidden sewer, then stood as a permanent monument to that shared effort, a shared asset from which everyone drew benefit. This created a powerful, self-reinforcing cycle. The project built unity, and that unity maintained the project for centuries. It embedded the infrastructure not just in the ground, but in the very cultural fabric, making its care a point of communal pride and responsibility. Of course, this picture is complex. We must also acknowledge that alongside these communal models, many ancient projects, including parts of Rome's aqueducts or the grand monuments of Egypt, relied heavily on systems of forced labor and slavery. This presents a difficult ethical tension, a reminder that the glorious, enduring works of the past were often built on profound human hardship. The principle, however, remains distinct. It shows that for infrastructure to be truly sustainable, it must ultimately be for the people, and ideally built by the people in some collective sense. The forced labor model often sowed resentment and required constant coercion, while the collective model fostered ownership and long-term stewardship. This distinction prompts a crucial question for our own time. How do we mobilize genuine collective effort for public goods today? We no longer have a labor tax, and rightly so, but we often struggle to cultivate that same sense of shared mission for maintaining our bridges, updating our grids, or cleaning our waterways. Is it through taxation that feels disconnected, or through volunteerism that can be fleeting? The ancient model suggests that the most resilient networks are those that people feel they have a direct hand in creating and preserving. It argues that the social cohesion, the sense of common purpose, is not a side effect of great building, it is the essential engine. Without that shared belief in the project, the blueprints remain just ink on parchment. The silent, flowing systems beneath ancient cities were, in the end, a testament to what human communities can achieve when they align around a common, vital need. They remind us that sustainability is as much about the bonds between people as it is about the pipes between places. The palace at Knossos was a marvel of water and light, a labyrinth with a secret heartbeat of flowing pipes. Within its walls, over 3,000 years ago, engineers crafted a drainage system of pipes so advanced it would not be matched in Europe for well over a millennium. These were not simple channels, but interlocking, tapered sections that fit together to create a sealed, pressurized flow, capable of carrying both in and out with elegant efficiency. They serviced elaborate bathrooms, flush toilets, and even a sophisticated storm drainage network, all integrated into the very fabric of the palace. This was not crude utility, it was a technological art form, a testament to a society that understood comfort, hygiene, and the hidden mechanics of a grand urban space. Then, around the year 1600 before the Common Era, the volcanic island of Thera, over 100 miles to the north, exploded in one of the most catastrophic eruptions in human history. The cataclysm sent tsunamis crashing against the shores of Crete, blanketed its fields in ash, and likely triggered a societal collapse from which the dazzling Minoan civilization never fully recovered. The palaces were abandoned, their populations scattered. And with that dispersal, something profound and quiet occurred. The knowledge embedded in those tapered pipes, the understanding of gradients and seals and integrated sanitation, simply faded away. The technology did not evolve or spread, it vanished. This event underscores a chilling and often overlooked principle, the vulnerability of knowledge itself. A society's technological sophistication is not a permanent possession. It is a living tradition, a flame that must be carefully tended and passed from hand to hand. When the civilization that nurtured it fragments, that flame can be snuffed out, leaving darkness for centuries. The intricate plumbing of Knossos became a ghost in the walls, a forgotten standard. In its absence, much of Europe would spend the next 2,000 years grappling with far more primitive solutions, relearning through painful trial and error the very public health lessons the Minoans had already mastered. This historical amnesia forces a direct and uneasy reflection. How do we, in our own time, preserve and transmit the critical engineering knowledge that sustains our world? We have moved from clay tablets to vast digital servers, believing our records are immortal, but are they? Digital data is fragile, vulnerable to corruption, format obsolescence, and the simple failure of the power grids that give it life. A catastrophic societal shift could render our most sophisticated blueprints as unreadable as linear a script was to later Greeks. The loss of the Minoan systems teaches us that true sustainability has a crucial, fragile dimension beyond pipes and cisterns. It is the sustainability of knowledge across generations. It is about creating robust, redundant ways to pass on not just the what, but the why, the deep principles of working with water, gravity, and community. This is the fragile thread in human history, the continuous story we must keep telling, lest the solutions of our ancestors and our own become mere mysteries buried in the dust. Waiting for some future age to painfully rediscover what we once knew so well. The vanished pipes of Knossos are a stark warning about the fragility of knowledge. But what about the systems that were deliberately built to endure the very collapse of order? This introduces a 10th, often overlooked principle, the role of hidden infrastructure in security and defensibility. For ancient planners, sustainability was not just about managing resources during peaceful, prosperous times. It was about ensuring a city could survive when those times ended. When the gates were closed and enemies stood outside the walls. In these moments, the most vital systems were not the grand temples, but the ones buried deep below, designed with a dual purpose, civilian utility in peace, and a strategic lifeline in conflict. The underground cities of Cappadocia, are the ultimate expression of this. Their miles of tunnels, rolling stone doors, and independent air and water supplies were not merely expanded basements, they were engineered refuges. Entire subterranean citadels, where a regional population could vanish from sight and withstand a prolonged siege. Similarly, Constantinople's vast, cathedral-like cisterns, like the Basilica Cistern, were more than just water storage. They were a calculated component of imperial defense. By holding a supply of fresh water within the city's formidable walls, Byzantine engineers removed a besieging army's most powerful weapon, thirst. A city could hold out for months if it had food, but only for days without water. These hidden reservoirs turned the city into a self-contained fortress, negating an enemy's strategy of encirclement and starvation. This principle of dual-use design reveals a profound layer of ancient urban thought. Planners were not just solving for sunshine and harvest, they were solving for shadow and siege. They thought in terms of multiple, overlapping futures, and they wove the solutions for the worst-case scenarios directly into the city's foundational fabric. The cistern was a public utility and a military asset. The underground tunnel was a storage space and an escape route. The fortified aqueduct channel outside the walls could be cut in crisis. But the stored water inside would see the people through. This mindset moves beyond simple environmental balance into the realm of strategic resilience. It asks, how does a city endure deliberate, targeted disruption? In our own era, the nature of the threat has transformed, but the core question remains painfully relevant. We no longer fear armies tunneling under our walls, but we are increasingly vulnerable to other kinds of sieges: cyber attacks on power grids, disruptions to satellite networks, or interference with water treatment systems. Our critical infrastructure is often centralized and digitally managed, creating single points of failure that ancient engineers would have found baffling. Their model suggests a different approach, one of distributed, redundant, and sometimes analog security. How do we design a modern electrical grid so that a failure in one node doesn't cascade into a regional blackout? Could we create backup water supplies that are physically isolated from digital control systems? The ancient principle is not about building bunkers, but about building in layers of assurance, making the vital flows of a city difficult to fully sever. It teaches that true sustainability is not a passive state of balance, but an active capacity to absorb shock, to have a plan buried deep within the system for when the world above turns hostile. This defensive layer was the final, crucial element in the ancient urban blueprint, ensuring that a city's life could persist even when its normal rhythms were violently interrupted. The silent, defensive layers of a city required a constant, reliable flow to function, and that flow often arrived through humble channels. Across the Aegean, in the bustling heart of classical Greece, engineers perfected a different kind of hidden network. In cities like Athens and Olympia, the lifeblood of the community did not thunder across majestic arched bridges, but traveled quietly beneath the streets through intricate webs of pipes. These were not the monumental aqueducts of a later empire, but a beautifully pragmatic solution for smaller, hilltop cities. The system was elegantly straightforward. Springs or large cisterns captured water from the scarce rainfall, and from these sources, a branching network of pipes carried it downhill by gravity to its vital destinations. The water would emerge at public fountains, where citizens gathered to fill their jars, or feed the essential baths and gymnasiums that were centers of social and civic life. This was infrastructure designed for direct, democratic access, bringing a fundamental resource to the people in their daily spaces. The true ingenuity, however, lay not in the grand concept, but in the meticulous craft of the pipe itself. Each section was carefully shaped from clay and fired in a kiln, but they were not simple, uniform tubes. They featured a brilliant design, flanged joints. One end of each pipe was shaped with a widened, flared collar, while the next pipe would slide snugly into this socket. The joint was then sealed with wet clay, creating a watertight connection that could still accommodate slight shifts in the earth without cracking. This was more than good pottery, it was standardized manufacturing. Pipes of consistent diameters and lengths could be produced in quantity, stored, and used as needed across the city. This modular approach represents a quiet revolution in urban thinking, the principle of replicable, interchangeable components. It transformed infrastructure from a bespoke, monumental art into a scalable, repairable system. If a section of pipe cracked, it could be dug up and replaced with an identical piece from stock, without having to reshape an entire channel from stone. Expanding the network to a new neighborhood meant simply producing more of the same proven units and linking them into the existing grid. This is an early form of industrialized building, applying the logic of the workshop to the scale of the city. It prioritized ease of maintenance and graceful expansion over immutable grandeur. The pipe network of a Greek city invites a direct comparison to our own modern dilemmas. So much of our contemporary infrastructure feels monolithic and custom, from unique bridge designs to proprietary utility components. When something fails, repairs can be slow, expensive, and require specialized parts that may no longer be made. The Greek model suggests a different philosophy, one where critical systems are built from standardized, open-source components. Imagine a future where sections of smart water main, modular solar microgrids, or even certain bridge segments are designed to universal specifications, allowing any city to repair or expand its systems quickly using interchangeable parts from multiple suppliers. This is not a call for bland uniformity, but for intelligent interoperability, building resilience into the very design language of our pipes and wires. The humble, flanged pipe, buried beneath the feet of philosophers and athletes, carries a lesson that is both ancient and urgently modern, that the most sustainable systems are often those built not as immortal monuments, but as adaptable, repairable assemblies. Yet the most resilient systems were not merely hidden, they were sometimes proudly, beautifully revealed. This introduces an 11th, transformative principle, the aesthetic integration of infrastructure into public space. For the Romans, the endpoint of their magnificent aqueducts was not a hidden tank, but a public celebration. The water emerged in grand, ornate structures called monumental fountains that were architectural wonders. These were not simple spouts, but multi-story facades adorned with statues of gods and nymphs, with water cascading over tiers of marble into broad, shimmering basins. The Nymphaeum was a deliberate, dazzling display of abundance. It shouted to every citizen that the city's lifeblood was not just secure, but overflowing, a gift to be enjoyed by all. This was infrastructure as civic theater, transforming the purely functional delivery of water into an experience of communal pride and sensory delight. Even the Cloaca Maxima, the Great Sewer, found its way into the city's aesthetic fabric. Its main outlet into the Tiber River was sometimes framed by monumental arches, incorporating the necessary exit of waste into the dignified architecture of the riverfront. This was a profound statement. Utility and beauty were not opposing forces, but could be woven together. By making the infrastructure beautiful, the engineers and planners accomplished something brilliant. They fostered public care and appreciation for the systems that served them. A stunning fountain was not just decoration. It was a daily, visceral reminder of the aqueduct's value. It turned the anonymous flow of water into a beloved landmark, something the community would naturally want to protect and maintain. This principle asks a quiet but powerful question of our own urban landscapes. How do we treat the necessary organs of our modern cities? We often relegate water treatment plants, electrical substations, and ventilation towers to the urban fringe, hiding them behind chain-link fences or bland concrete walls. Treating them as industrial embarrassments. The ancient model suggests a different path, one where these essential nodes are designed with consideration for their place in the community. Could a water recycling facility also be a park with educational wetlands? Could a power substation be integrated into the base of a public sculpture or a building with a green facade? This is not about frivolous decoration, but about acknowledging that the things which sustain us deserve a place of honor in our visual and social environment. When infrastructure is beautiful, it ceases to be an invisible nuisance and becomes a point of civic identity. It encourages stewardship because people value what they can see and admire. The Roman Nymphaeum teaches that the ultimate success of a system may lie not only in how well it works, but in how deeply it is loved. Beneath the sun-drenched marble of a Roman forum, a hidden world of shadow and cool stone performed its quiet, essential work. While citizens debated politics and conducted business in the open air above, their footsteps echoed over a remarkable feat of engineering known as the. This was a semi-subterranean gallery, a long, barrel-vaulted corridor partially buried in the earth. It was not a basement or a cellar in the ordinary sense, but a deliberately designed interstitial space, a hidden layer woven between the city's public face and its foundational earth. These galleries served a stunning array of purposes, all at once. Their primary gift was environmental control. The thick earth surrounding them and their vaulted stone ceilings created a naturally cool, stable, and dry climate, perfectly suited for storing perishable goods. From sacks of grain and amphorae of olive oil to precious state archives that needed protection from damp and heat, but they were far more than just storage rooms. They also functioned as discreet passageways, allowing priests, officials, or servants to move between temple complexes and public buildings unseen, without disrupting the ceremonies or commerce unfolding in the sacred spaces overhead. This hidden circulation was of urban choreography, separating the practical backstage movements from the public performance of civic life. Furthermore, and perhaps most ingeniously, they often acted as a massive structural foundation. By creating a solid, continuous platform of vaults, it could level uneven terrain, providing a stable, raised base upon which to construct the grand temples and colonnades of the forum. A single architectural element was thus doing triple duty. It was a climate-controlled warehouse, a secret corridor, and the very skeleton supporting the city's most important public square. This is the principle of multi-layered functionality pushed to its elegant extreme. There was infrastructure as architectural backbone, an unseen element whose very existence enabled the grandeur and complexity of the world above. It represents a philosophy of profound efficiency, where every cubic foot of space and every ton of stone was asked to perform multiple roles. There is a quiet genius in this integrated design that challenges our modern compartmentalization. Today, we tend to design buildings with dedicated, single-purpose spaces, a basement for mechanicals, a separate storage room, a distinct service corridor. The Roman asks us to consider a more holistic approach. What if the foundational structures of our buildings, the parking garages, the utility tunnels, the support plinths, were consciously designed to be more than just voids? Could they also be insulated community spaces during extreme weather, secure pathways for urban wildlife, or even galleries for public art. This ancient model suggests that the most sustainable architecture thinks in terms of nested functions, where the unseen parts are not afterthoughts, but active, intelligent participants in the life of the structure. It is a lesson in architectural economy that whispers from beneath the marble, urging us to build with layers of intention, where every hidden gallery holds the potential for multiple lives. Yet even the most beautifully integrated systems carried within them the seeds of their own potential undoing. For every aqueduct that flowed for centuries, there was a canal that silted shut, a reservoir that cracked, or a water source that slowly dwindled to nothing. The hidden infrastructure of the ancient world offers us not only blueprints for success, but also sobering, invaluable records of failure. This 12th principle is perhaps the most humbling, learning from collapse. These silent breakdowns teach us about limits, about unintended consequences, and about the delicate, often invisible line between a city's triumph and its slow retreat back into the landscape. Consider the great city of Cahokia, which flourished along the Mississippi River near present-day St. Louis over 1,000 years ago. At its peak, it was a bustling metropolis of perhaps 20,000 people, centered around enormous earthen mounds. Its success was built on a sophisticated agricultural system and a complex social order. Yet by the 14th century, the city was largely abandoned. While the reasons are complex and debated, one compelling thread points to a hidden infrastructure failure, not of stone, but of wood and water. To build their monumental mounds and their vast palisade walls, they required immense quantities of timber. This likely led to widespread deforestation of the surrounding bluffs. Without tree roots to hold the soil in place, erosion would have accelerated dramatically. Torrents of silt, washing off the denuded hillsides with every rain, could have choked the local creeks and sloughs they relied upon for fishing and transportation, while also degrading the fertile farmland below. They may have, quite literally, sawed off the branch they were sitting on, altering their microenvironment in ways that made sustained, dense settlement unsustainable. Similarly, at the stunning cliff dwellings of Mesa Verde in the American Southwest, a thriving ancestral society mastered water capture in an arid land, building check dams and reservoirs to channel scarce rainfall. Yet research suggests that a combination of prolonged drought and the very agriculture that sustained them may have led to critical topsoil loss. Their fields situated on the mesa tops could have gradually eroded, reducing yields just as climate patterns shifted against them. In both cases, we see a pattern, a society pushing its engineered systems and its local environment to, and perhaps past, a breaking point. The failure was rarely a single dramatic event, like an invading army. It was more often a slow, creeping crisis, a series of small, compounding choices whose collective impact only became clear generations later. The dam did not burst, it silted up. The forest did not burn, it quietly vanished. The soil did not rebel, it simply washed away, one grain at a time. These ancient collapses are not stories of stupidity, but of complexity. They represent experiments in urban living, where the variables of resource use, population pressure, and climate change interacted in ways the planners could not fully foresee. Their sophisticated systems worked brilliantly until they didn't. This historical hindsight is a form of priceless data for our own time. It emphasizes a need that they could not have formally articulated, the need for what we now call environmental impact assessment, a conscious effort to look decades or centuries down the chain of consequences. How do we today recognize our own warning signs? Our challenges are global in scale: climate change, aquifer depletion, plastic pollution, but the principle remains hauntingly local. Are we over-pumping a groundwater basin, causing the land itself to sink? Are we constructing in a floodplain that has been dry for a generation, forgetting its ancient rhythms? Are we relying on a single, vulnerable source for a critical resource? The failures of Cahokia and Mesa whisper that sustainability is not a fixed state achieved by brilliant engineering alone. It is a continuous, dynamic negotiation with the living systems that support us. It requires building not just for abundance, but with a profound respect for thresholds, for the invisible lines that, once crossed, trigger a cascade of decline. These abandoned cities are not just ruins, they are the most solemn classrooms we have, teaching that the ultimate test of any hidden network is time. And that time always reveals the true cost of ignoring the limits of the land. The silent geometry of an aqueduct began not with a shovel, but with a surveyor's gaze. Before a single stone was laid for those flowing highways, ancient engineers faced a monumental puzzle: how to trace a perfect, gentle downhill slope across 50 miles of rugged, unseen terrain. Using nothing but sunlight, water, and simple wood, their tools had names that sound almost mythical to modern ears. There was a cruciform device mounted on a pole, with plumb bobs hanging from the ends of its crossarms. By sighting along these weighted lines, a Roman surveyor could establish perfectly straight lines and right angles across the landscape, laying out the initial path with astonishing accuracy. But the true marvel was a wooden bench over 16 feet long with a shallow groove carved along its top. The surveyor would fill this groove with water, nature's perfect level. By sighting along the still surface, they could determine if the ground was truly flat, or calculate the minute gradient needed for water to flow, a drop of perhaps only 1 foot for every mile of channel. This was technological humility achieving the sublime. There were no laser rangefinders, no satellite signals, only a profound understanding of geometry and the immutable laws of physics, harnessed with patient, iterative observation. The intellectual achievement here is staggering. These engineers were not just builders, they were applied mathematicians and physicists, translating abstract principles into tangible, flowing reality. They understood that water seeks its own level, and they used that single, simple truth to orchestrate the movement of entire rivers across continents. This mastery of surveying was the invisible first step, the quiet act of calculation and vision that made every visible aqueduct and every hidden sewer possible. It forces a reflective question about our own era of digital dependency. We rely on global positioning systems and computer-aided design to perform tasks these engineers did with a plank and a puddle of water. Could we, if pressed, retain such fundamental skills? The principle at work is not about rejecting technology, but about preserving the deep, intuitive understanding that our tools are meant to augment. The ancient surveyor had to internalize the landscape, to feel the gradient in his bones, because his instrument offered no digital readout, only a reflection of the world as it truly was. This intimate, physical dialogue with the environment is a form of knowledge we risk outsourcing entirely to our devices. Their work stands as a testament to a different kind of ingenuity, one rooted not in processing power, but in perceptual power. In the human capacity to see the hidden lines of force in the world, and to draw upon them with elegant, minimal means. It reminds us that the greatest infrastructures begin not with concrete, but with contemplation, a silent conversation between a mind and a horizon that lays the blueprint for everything to come. The surveyor's calculations were a form of secular devotion, but for many ancient societies, the act of building was itself a sacred covenant. This brings us to a 13th, deeply human principle, the role of religion and ritual in sanctifying infrastructure. The practical networks of water and stone were not seen as merely functional. They were often understood as gifts from, or channels for, divine forces. A spring was not just a hydrological feature. It was the home of a nymph or a naiad, a spirit to be honored and appeased. The Romans consecrated their aqueducts to specific deities, and the endpoint of that water in a nymphaeum was as much a shrine as a fountain. In Persia, the construction of a qanat, that life-giving water mine, was frequently accompanied by ceremonies. The choice of the mother well's location, or the celebration of the water's first emergence, might involve prayers and offerings, recognizing the profound mystery of drawing a river from the heart of a dry mountain. This fusion served a brilliant, practical purpose. It tied the utterly essential work of survival to the deepest layers of cultural meaning and spiritual belief. By making a water source sacred, you ensured it was treated with reverence, not just utility. It became taboo to pollute a spring dedicated to a goddess, or to neglect the maintenance of a canal that was seen as the physical manifestation of a god's favor. Infrastructure was embedded in the religious worldview, making its care and preservation a sacred duty, a communal obligation to the divine. This provided a motivation far more powerful than any civic ordinance could be. A king's decree might be forgotten, but a god's law was eternal. The spiritual dimension added an invisible layer of resilience, protecting the physical systems through the steadfast power of shared belief and ritual practice. It transformed the engineer and the maintenance worker into stewards of a holy trust. Our modern approach is, of course, largely secular and scientific. We understand the hydrologic cycle and the principles of fluid dynamics. We maintain our water systems because we must, not because we fear divine retribution. Yet this ancient principle poses a quiet, profound question for our time. In the absence of nymphs and water gods, how do we cultivate a similarly deep, non-negotiable cultural value for the hidden systems that sustain us? How do we move beyond seeing pipes and wires as mere utilities, and instead recognize them as the vital, collective inheritance of our civilization, worthy of reverence and unwavering care? The answer may not lie in inventing new myths, but in fostering a different kind of sacred understanding, one rooted in the science of interdependence and a shared ethical duty to future generations. It is about rebuilding that sense of sacred duty, not to a deity, but to the community and the planet itself, ensuring that what we build today is treated not as disposable, but as a legacy to be protected with something akin to devotion. The sacred duty of maintaining a city's water was mirrored by another, equally pragmatic form of devotion, the worship of commerce. For the lifeblood of an ancient metropolis was not only water, but grain, oil, wine, and marble, the material wealth that flowed from across a known world. This torrent of goods required its own hidden infrastructure, a network of storage and movement as meticulously engineered as any aqueduct. At the port of Ostia, where the Tiber River met the sea, the visible chaos of docks and markets was underpinned by a silent, subterranean world of astonishing efficiency. Beneath the warehouses, known as the ground, was not solid earth. Engineers constructed raised floors, suspending the storage platforms on a forest of small brick pillars. This created a continuous air cavity beneath the entire warehouse floor, a brilliant passive system that allowed air to circulate freely, preventing dampness, discouraging rodents, and keeping precious stores of Egyptian grain or Spanish olive oil from spoiling in the humid Italian climate. This was climate control achieved through architecture, not machinery. The design did not stop at the floor. There were fortresses of commerce, with thick, windowless walls to deter theft, and intricate internal layouts that allowed for the systematic organization of goods. Cranes powered by human treadmills, a technology that would seem familiar centuries later, swung cargo directly from ships' holds into these vast storage halls, minimizing handling and loss. The port itself was a monument to logistical ambition. Breakwaters of concrete that cured underwater created calm harbors in the open sea, while lighthouses like the famed Pharos of Alexandria, one of the wonders of the ancient world, guided ships safely to shore with flames reflected by polished metal mirrors. This entire complex, from the submerged concrete to the ventilated floors, operated on a single, powerful principle: the minimization of friction in trade. Every delay, every spoiled shipment, every sunken vessel represented a cost, not just in coins, but in the stability of a city that relied on imported food to feed its million citizens. The hidden infrastructure of commerce was the empire's circulatory system, and its efficiency determined the heartbeat of Rome. This ancient network of optimized logistics prompts a direct comparison to our own globalized world. We have container ships of staggering scale and automated ports that move cargo with robotic precision, achieving a level of throughput the Romans could scarcely imagine. Yet this efficiency often comes with immense, hidden costs in carbon emissions from shipping and trucking, in the vulnerability of hyper-specialized supply chains to sudden disruption, and in the treatment of the landscapes around our ports as purely industrial zones. The Roman model, for all its reliance on human and wind power, integrated its commercial hubs into the urban fabric. Ostia was a thriving city in its own right, not an isolated logistical park. Their principle of reducing friction was not just about speed, but about reliability and resilience over vast distances. It asks us whether our own commercial arteries, for all their visible might, have lost something in their hidden design, a capacity for graceful adaptation when the winds of trade shift unexpectedly. The silent, pillared floors of Ostia's warehouses held up more than sacks of grain. They held up an entire urban way of life, proving that a city's true foundations were as much about barrels and bushels as they were about bricks and mortar. A public fountain bubbling in a Roman square was a promise of equality, but the pipes running beneath the city streets told a more complex story. This reveals a 14th, deeply human principle: the tension between equity and access in every hidden network. While the grand aqueducts were celebrated as public works, their distribution was a mirror held up to society's hierarchies. The water did flow to all, in a sense. Immense public baths, like the baths of Caracalla, offered hygiene and social space to citizens across the economic spectrum, funded by the state or by wealthy patrons. Countless street fountains provided the daily drinking and cooking water for the vast majority of Rome's inhabitants, who lived in crowded apartment blocks without private plumbing. This was a monumental achievement in public health and social welfare, a recognition that a city's stability depended on a baseline of shared resources. Yet alongside this public bounty, a separate privileged channel existed. Lead or pipes branched off the main lines, carrying a private, uninterrupted flow directly into the villas of the wealthy and the estates of the powerful. For them, water was not a communal gathering point, but a domestic convenience, a luxury that literally flowed indoors. This dual system reflects a recurring truth about infrastructure: it is never neutral. Its design always answers a fundamental question: who is it truly for? The Roman model provided a basic, life-sustaining floor for the many, while offering a tier of enhanced comfort and autonomy to the few. The infrastructure did not create the social inequality, but it did concretize it, baking privilege into the very plumbing of the city. We see this principle echoed in other forms. The wide, straight processional avenues of imperial cities were designed for the movement of armies and the parades of rulers, first and foremost. The secure, subterranean passages facilitated the discreet movement of elites, not the common populace. This is not to dismiss the immense public benefit of these works, but to recognize their layered purpose. They served the state, they served the public, and they served the powerful, often in that order. This ancient tension forces a direct and urgent question for our own era of so-called smart cities. When we embed sensors in our streets and algorithms in our grids, who do they most intelligently serve? Does a dynamic traffic management system prioritize emergency vehicles and public transit, or does it subtly optimize routes for premium subscription services? Does a data-driven utility network ensure stable, affordable service for all neighborhoods, or could it lead to differentiated tiers of reliability? The principle of equity asks us to look past the gleaming technology to the underlying values coded into its design. The Roman aqueduct, for all its stone and water, was also a political document, a statement about who deserved access and in what measure. Our digital infrastructures are no different. They hold the potential to democratize services and information like never before, or to create new, invisible walls of exclusion. The lesson from the ancient pipes is that the most sustainable system is not merely the most efficient one, but the one that most consciously serves the collective good. It reminds us that the final measure of any hidden network, whether of water or data, is not just how well it flows, but how fairly it reaches every corner of the city it claims to sustain. 4,000 years before the modern skyscraper, a city rose from the floodplains of the Indus River with a vision so complete it feels eerily contemporary. One of the great capitals of the Indus Valley civilization did not grow haphazardly. From its very first brick, it was executed according to a master plan of astonishing foresight, a preconceived blueprint where infrastructure was not added later, but served as the city's foundational skeleton. This is the principle of holistic master planning in its most ancient form. The evidence is in the very bones of the city. Its streets run in a precise, unwavering grid, with wide main thoroughfares intersecting at perfect right angles, dividing the urban space into orderly blocks. This geometric rigor was not for aesthetics alone, it was a logistical. It created predictable pathways for everything, from foot traffic to the flow of water and waste, making the entire city legible, navigable, and crucially serviceable. Even more telling is the humble brick. Across the entire city, from the foundations of the grandest structure to the walls of the most modest home, the baked clay bricks are of a standardized size and proportion. This uniformity speaks of a centralized authority, a governing body that imposed a common standard of construction for the entire community. It meant that construction and repair could be systematic, that materials were interchangeable, and that the very fabric of the city was built to a shared, resilient code. But the true genius of the plan lies beneath those orderly streets. Running under the grid, often hidden from daily view, was a network of covered drains and sewers, constructed with those same uniform bricks. Nearly every street had one, and they connected to larger, main channels that carried away from residential areas. This was sanitation engineered into the city's DNA from day one. Homes, even smaller ones, often featured bathing areas with drains that fed directly into this subterranean network. At the city's heart stood the Great Bath, a massive, waterproofed public tank built with a layer of bitumen, a natural tar to prevent leaks. It was likely a center for ritual purification, but it also stands as a monument to the civilization's hydraulic expertise, a public utility designed for communal use. The totality of this design suggests a society that thought in terms of systems, not just structures. They planned for the health of the body politic by planning for the health of the individual body. Ensuring clean water and waste removal were communal rights embedded in the urban form. The apparent social harmony and remarkable longevity of, which thrived for centuries, suggest this comprehensive approach worked. It created a resilient, hygienic, and orderly environment that supported a large, dense population. This ancient blueprint forces a direct and challenging question upon our own era of urban expansion. When we plan new cities or retrofit old ones, how often do we begin with such a complete, integrated vision? Too often, our urban growth is piecemeal, a patchwork of private developments where utilities are an afterthought, tacked on after the houses are built. Roads curve for aesthetic appeal, but create inefficient, convoluted routes for emergency services and public transit. Planners understood that the city is a single organism, and its circulatory, nervous, and skeletal systems must be designed in concert. What if we dared to plan with that same holistic boldness today, starting not with the sale of individual plots, but with the laying of a resilient, interconnected grid for water, energy, data, and green space? The silent, geometric streets of are more than an archaeological wonder. They are a quiet argument for the power of starting with the end in mind. Proving that the most sustainable city is often the one that was conceived, from its very first moment, as a complete and integrated whole. The orderly grid of was a triumph of human design, but no blueprint could ever fully silence the unpredictable power of a river in flood. This introduces a 15th vital principle, the interface with nature, specifically the ancient art of flood management. For cities built along the life-giving banks of the Tigris, the Nile, or the Yellow River, the annual inundation was a paradox, a source of fertile silt and a potential agent of catastrophic destruction. The solution was not to defeat the water, but to negotiate with it, to build systems of resilient design that accommodated natural cycles rather than trying to permanently eliminate them. This required a patient, generational observation of patterns, a deep reading of the land's own rhythms. In ancient Babylon, engineers did not just build walls against the Euphrates, they built a sophisticated system of levees and diversion channels. These earthworks acted like a pressure valve, guiding excess floodwaters away from the urban core and into designated overflow basins, protecting the city while still allowing the river to perform its essential soil renewing work. A world away, on the arid north coast of Peru, the Moche civilization faced a different, terrifying water event, the irregular but devastating floods brought by the El phenomenon. Their response was a masterpiece of anticipatory engineering. They constructed extensive networks of canals, but these were not just for irrigation. The canals were designed with a dual purpose: to capture and distribute scarce water in dry years, and to safely channel and dissipate the torrential, destructive surges of an El event when it arrived. They built flexibility into the landscape itself, creating a system that could function in two completely different hydrological regimes. This principle is not about control, but about choreography. It recognizes that water cannot be commanded, only respectfully guided. It required a humility before natural forces, an understanding that the city must yield in some places to remain intact in others. This ancient wisdom speaks with acute urgency to our own era of climate change and rising sea levels, where the strategy of simply building higher walls and stronger barriers is increasingly proving to be fragile and fantastically expensive. The question posed by the Moche canals and Babylonian levees is profound. How can we design our modern cities to be porous and adaptive to water, to live with floods rather than in constant fear of them? This might mean reclaiming floodplains as parks that can safely absorb overflow, designing buildings with ground floors meant to get wet, or creating green infrastructure that slows and absorbs stormwater before it ever reaches a pipe. It is a shift from a mentality of resistance to one of resilience, learning to design spaces that can gracefully accept the inevitable surge and then recover. This respectful, adaptive dance with nature, forged over generations of observation, was not a secondary consideration for these ancient societies. It was the key to their long-term survival in landscapes they knew they could not fully conquer. A city's walls were only as strong as its deepest well. In the sun-baked plains of the Greece, the Mycenaean citadel of stands as a fortress of Cyclopean stones, its walls so massive later Greeks believed they were built by giants. Yet its true defensive masterpiece lies not in these towering ramparts, but in a breathtaking feat of subterranean daring. Carved down through 20 meters of solid rock, a secret staircase descends into darkness. Its walls are built with the corbel technique, each stone slab jutting slightly over the one below, forming a narrowing tunnel that seems to swallow the light. At the bottom of this dizzying shaft lies not a tomb, but a treasure more precious than gold, a vast, hidden cistern, perpetually filled by a spring whose source lay safely outside the fortress walls. An underground conduit, a hidden artery of stone, secretly channeled that external spring water into this guarded interior pool. This was infrastructure as a strategic secret, a lifeline deliberately concealed from any enemy who might lay siege. While attackers camped outside, confident they could starve the citadel out by cutting off its visible wells, the defenders had a private, secure reserve, a cool, dark abundance known only to them. It embodies a principle of profound martial cunning, redundancy through secrecy. A backup system is only useful if your enemy does not know to target it. The water in that cistern was more than hydration. It was hope, it was time, it was the power to outwait an enemy under the blistering sun. This martial application reveals how the stark imperative of survival, the pressure of conflict, could drive some of the most clever and concealed designs. The staircase is not merely architecture, it is a lesson in psychological warfare, a silent bluff built into the bedrock. It prompts a direct and unsettling question for our own interconnected world. Do our modern cities possess similar redundant, secured systems for essential resources? We have backup generators and secondary data centers, but are our water supplies, our power grids, our digital networks truly protected by layers of secrecy and physical isolation? Or are their vulnerabilities mapped and visible to any potential adversary? The silent cistern of whispers that true resilience often lies in what remains unseen and unknown, a lesson in preparing for the worst by hiding your best. That hidden cistern held its secret for over 3,000 years. Yet the greatest secret of ancient infrastructure was not how to hide it, but how to remember it. The 16th principle woven through all these stories is one of legacy and cyclical rediscovery. The meticulous engineering that sustained Rome did not vanish forever with its empire. 1,000 years later, in the intellectual awakening of the Renaissance, European scholars and architects began to unearth and translate long-forgotten Roman texts. The work of Sextus Julius, the curator of Rome's waters, was studied not as a historical curiosity, but as a vital technical manual. His precise documentation of gradients, pipe diameters, and maintenance schedules became a revelation. Here was not myth, but method, a detailed record of how to build a city that worked. This rediscovery was a profound moment in human thought, a reconnection with a lost strand of practical genius. It sparked a renewed fascination with arches, aqueducts, and public baths, principles that began to reshape the burgeoning cities of early modern Europe. This cycle repeated with the Industrial Revolution, as engineers grappling with the explosive, filthy growth of new metropolises like London and Paris looked back to Roman sanitation for inspiration. They saw in the Cloaca Maxima a model for the vast, subterranean sewer networks they desperately needed to combat cholera and typhoid. This is not mere imitation, it is a historical dialogue. The past becomes a living laboratory, offering time-tested answers to challenges we mistakenly believe are uniquely our own. We see this dialogue everywhere in our modern urban fabric. The permeable pavement now used to manage stormwater runoff in sustainable cities functions on the same principle as the gaps between ancient cobblestones, allowing rain to seep into the earth rather than overwhelm drains. The engineered soil and vegetation layers of a contemporary green roof perform the same cooling, water-absorbing function as the legendary Hanging Gardens of Babylon, moderating a building's temperature and reducing the urban heat island effect. Modern distributed solar microgrids find a philosophical ancestor in the decentralized Qanat systems, both creating resilient, local sources of essential energy, one of water, one of power. Rather than relying solely on a fragile, centralized supply, this principle encourages us to look back not with nostalgia, but with a pragmatic eye for adaptation. The ancient solutions provide the logic, the underlying pattern of working with natural forces. Our new materials, polymers, composites, photovoltaics, allow us to execute that logic with greater efficiency and scale. The lesson is that human ingenuity is not a straight, ascending line, but often a spiral. We advance, we forget, and we are forced to rediscover foundational truths in new contexts. This cyclical nature of knowledge is humbling and empowering. It tells us that when we face a seemingly insurmountable urban crisis, whether it is water scarcity, waste management, or resilient design, we are almost certainly not the first to confront it. The archives of stone and clay hold a deep library of experiments, some triumphant, some tragic. Engaging in this historical dialogue does not mean copying the past, but conversing with it, asking how its timeless principles of gravity, flow, community, and passive design can be translated through the lens of our current technology and values. It enriches our practice by freeing us from the illusion that every solution must be invented from scratch, and instead allows us to stand on the shoulders of giants who looked at the same sun, felt the same pull of the earth, and solved for the same essential human needs. The spiral of rediscovery brings us to this moment, a moment of profound urban challenge and possibility. We stand in cities of glass and steel, facing crises of heat, water, and waste. Yet the most powerful solutions may not lie in a new invention, but in a very old realignment. The principles that guided water through Petra and cooled the halls of are not relics, they are a timeless toolkit for resilience. We can begin this synthesis now by looking at three specific ancient ideas ready for a modern rebirth. First, the principle of passive design. Ancient builders used orientation, thermal mass, and natural ventilation as their primary climate systems. A modern building can do the same, not by abandoning technology, but by letting its form do the initial work. Orienting structures to capture winter sun and block summer heat, using materials that absorb and slowly release warmth, and designing for cross breezes that minimize air conditioning needs. These are not new concepts, but applications of a solar logic mastered ago. Second, We must reclaim the water cycle at the smallest scale, just as the Nabateans did in their desert capital. Decentralized rainwater harvesting, where every roof and courtyard captures its own rainfall for non-potable uses, mimics their network of cisterns. Systems which reuse water from sinks and showers for irrigation echo the Roman practice of cascading water from fountains to latrines to sewers, using every drop multiple times before returning it to the earth. Cities like Singapore actively study these ancient hydrological models, creating a modern water system that treats every raindrop as a resource to be captured, cleansed, and reused in a continuous loop. Third, we must revive the ancient commitment to multifunctional public space. The Roman Forum was not just a plaza, it was a civic heart combining commerce, justice, religion, and social life. Our public spaces can be re-engineered with similar layered purpose. A city park should not be merely decorative. It can be a stormwater management basin, a community garden, a cooling green refuge, and a social hub all at once. This requires a shift in our very ethos of construction, valuing durability and long-term benefit over cheap, disposable speed. It means mandating materials and designs that last for generations, and seeing infrastructure not as a cost, but as a legacy. This is the call to merge the deep intelligence of the past with the precision tools of the present. We are not being asked to rebuild with mud bricks, but to rebuild with the wisdom those bricks embodied. The solutions are indeed beneath our feet, etched in the stones of forgotten conduits and encoded in the layouts of ancient grids, waiting for us to listen. Our future cities will not be sustainable because of a single miraculous technology, but because we remembered how to design in harmony with the enduring forces of sun, water, and community. 16 principles, each a quiet rebellion against the chaos of nature and the fragility of human community. We have traced the hidden veins of cities long silent, from the water mines of Persia to the ventilated warehouses of Rome. These were not random acts of construction, but a deliberate, multifaceted philosophy of survival. Sustainability, as these ancient engineers practiced it, was never a single technology or a lucky accident. It was a conscious choice, repeated across generations, to build systems in harmony with human needs and the unyielding limits of the natural world. It required the surveyor's precise eye, the community's collective labor, the planner's integrated vision, and the humble commitment to cleaning the pipes year after year. They built for the flow of water, the removal of waste, the storage of plenty, and the security of the community, understanding that a city is an organism, and every hidden artery must function for the whole to thrive. Their legacy is not merely in the ruins we excavate, but in the very idea that a city can be a pact between people and place, a designed agreement to live well together within the boundaries of a river, a desert, or a mountain. As we now face our own urban crises of heat, scarcity, and strain, these ancient voices offer a clarifying perspective. The most profound solutions may not lie in the next flashy breakthrough, but in returning to first principles, thoughtful, durable, and equitable design. Look at the city outside your window. What hidden systems bring it water and power and carry away what it no longer needs? How resilient are those systems, and who do they truly serve? The questions asked by a Roman curator of waters or a Nabatean tunnel digger are the same ones we must answer today. Their work, buried for centuries, reminds us that the foundation of a thriving future is not always about inventing something new. Sometimes, it is about remembering something very, very old. What forgotten wisdom lies beneath the streets of your own town? Share your reflections in the comments below. If you enjoyed this journey into the hidden layers of history, Subscribe for more explorations that connect the past's deepest mysteries to our present world. Thank you for watching, and remember, the blueprints for tomorrow are often etched in the stones of yesterday.